start. Welcome everyone to the Decarb December learning series. This is a series of webinars in the Decarbonization Business Charter. So, the DBC, which is Decarbonization Business Charter, was conceived to establish a unified platform that brings together key stakeholders, fostering collaboration for the decarbonization of the whole building and construction sector. This initiative is a collaborative effort between WRI India, World Resources Institute, Alliance for an Energy Efficient Economy, Mahindra Lifespace Developers Limited, and EcoCollab. This initiative aims to address shared challenges and opportunities in the decarbonization sector, and the charter provides a framework to identify and prioritize critical actions, steering efforts towards the common goal of reducing carbon emissions in the whole of the sector. So, through these webinars, we'll have the privilege of attending and engaging workshops led by some of the most foremost experts in the field. So, the webinar sessions are designed to provide practical insights and strategies for decarbonizing urban building sectors and paving the way for a more sustainable future. So, without further ado, I'd like to introduce today's speaker who will be speaking on demand flexibility of the residential sector. So, we have Dr. Professor Himanshu Jan here. So, he's an assistant professor in the Department of Hydro and Renewable Energy at IIT Roorkee. He has over 13 years of experience and combined research and industry experience, modeling and analyzing the impacts of integrating high levels of renewable energy in power systems. He holds a PhD, MS, and a BTech degree in electrical engineering from Virginia Tech, the University of Arlington at Texas, and the GB Pant University of Agriculture and Technology, respectively. So, sir, you can take away.
Thanks a lot, Soumya. Thanks a lot for the nice introduction. If you could just confirm that you are able to see my screen, then I'll just start.
Yeah, we can see your screen.
All right. A very good evening to all of you. What I'll do in the next hour or so is to give you a rundown on the need for deep electrification in our electric grid. And as a result of it, the need for increasing its flexibility so we can integrate more renewable energy, do so reliably, and the role that demand flexibility plays in increasing the flexibility of our entire grid as a whole. So I think this I'm pretty sure by this time you already know how much global warming is an issue across the globe, and we need to take urgent action for it. And this slide just reaffirms how average temperatures over the world have increased over the last 140-50 years. So you can see that as we move towards 1980s and beyond, we see a significant move towards this red shift that we see in the temperatures. The temperatures have gone up. So we are really at a point where we need to take urgent action so that we can include more renewable energy in our systems and move away from fossil fuels. As a result, what we have seen is that if we start from the 1800s, our energy systems were largely traditional biomass, transitioning to coal, oil, gas, and now we have started to add more solar, wind, hydropower, modern biofuels, and other renewables. And what we expect to see happen in the future, or at least that should happen, is we want these gas, oil, and coal to go down further and other renewables to go up. Now, one of the things that renewables do for you, unlike coal, oil, and gas, is you produce electricity from your major renewable energy sources. Today, it is solar, wind, and hydropower. And then that electricity is used for our end-use purposes, whether it's for lighting, for cooling, for heating purposes. That's where the trend is. And that is why we say that we are moving towards an energy system where deep electrification is key. So whether it's your transportation sector, whether it's your heating and cooling needs, your cooking needs, everywhere we want to move towards electricity as the source that provides us energy to do our end-use jobs. And the need for moving towards renewable energy is very urgent because as this chart shows you, that even if we assume that in 2023, the world as a whole achieves its peak carbon emissions, which is not the case, then it has to reduce the total emissions that we are producing each year as of today. For the next 6 7 years, it has to continuously reduce our emissions by the same amount, which is a huge task, because we emit around 37 billion tons of CO2 a year, and if we want to reduce that much amount for every year, that really takes a lot of effort. Especially if we look at how the energy mix has changed globally and in India over the last 22 years. I mean, if you look at India in particular, our energy mix has reduced, but not very rapidly. From 92% in 2000 to 89% in 2022, we are still using a huge amount of fossil fuels to power our energy needs. And that's pretty much the same for the entire globe as well. Therefore, the challenge is huge. I mean, how do we achieve that? Well, we need lots of money. And that is not something I'm going to talk about. I think I'll focus more on the technical aspects of things. We need to reduce our demand, and we need to electrify our demand, as I said, because renewable energy resources that are mature, the technologies that are commercially viable, they're very good for producing electricity, and then that electricity could be used to meet our energy needs. Of course, we need to produce electricity from low carbon technologies, and you all are very well aware of what those technologies are. Today, for India in particular, it's hydropower, solar, and wind right now. But at the same time, while we want to produce more electricity from renewable resources, we don't want to compromise on the reliability and resilience of the grid. And for that to happen, we want to make our grid much more flexible than what it is today. And even here, if you see, the transition to renewable energy resources has also been fairly slow. We are still using a huge amount of fossil fuels to power our electricity generation. In the 22 years, again, the same period as I showed before, we have come down from 83% to 77%. So 10% of that renewable energy that we are now generating, renewable electricity, comes from hydro, and rest is coming from your variable resources, which are wind and solar predominantly. So let me just stop here for a second and ask you, like, in case you have any questions for the first part before I move on to the more in-depth discussion on what these changes matter or how they affect our grid. So any questions before I move on? Okay. So when we talk about
Pradeep raised his hand.
Yeah,
Pradeep,
yes, please.
are you here?
Yes, good evening. My name is Pradeep Dhingra. I am a Critical Energy Auditor and this field. Mr. Jain, will you share this presentation on this, or it is your?
No, I'm fine. I mean, I can share it.
It's all right, Pradeep. I have put a email ID in the chat box. You can contact us there, and we'll send you the presentation.
So nice, madam. Thank you. Please continue. Please.
Sure. So when we talk about an electric grid, I mean, this is the kind of grid that we are most familiar with. It shows voltage levels that are from the United States, but structurally, the system has been the same for the last 100 plus years. So what happens in the grid is we start generating electricity from generating stations, transmit it over high voltage transmission lines, get down closer to our customers, and either provide directly voltage at high voltage levels to high power customers, your industries, for instance, or bring the voltage down and provide power to our homes, to commercial offices, buildings, and stuff like that. So if I were to ask someone in this audience how would you define this grid? What is your understanding of what are the defining features of this grid? What would be some things that come to your mind? Anybody wants to, just jump in and just provide some thoughts on these?
Anyone? So there's no show of hands.
Okay. All right. No worries.
Somebody has
Maybe,
said losses in
yes.
transfer.
Yeah, there are certainly, absolutely, you're right. There are losses in transfer of electricity. Um, but how I would characterize this grid is that, first of all, it's highly centralized. What it means is that you have very few plants compared to the number of customers to whom you are providing electricity. And those are very large plants, 500 megawatts, 1000 megawatts, even larger plants. Second aspect of our conventional power system is that we have controllable power output. We control how much fuel we put into our resource, into our generation asset, and then out comes the power that we want to generate. We can reduce the injection of fuel and the power output goes down. We can increase it, power output goes up. So you all know the drill. We also have a lot of inertia in our system, and that is coming from the rotating mass that connects to our grid. All the generators, turbines together, they're very heavy rotating masses that connect to the grid. And for some of those who are more into the electrical engineering side, we won't discuss this point very much. We also provide a lot of short circuit current. So what the silent sentinels of your grid, the protective relays, for instance, they are the ones that benefit from this capability of our current grid. What we are doing is that we are starting to move towards a different kind of a system. In this system, we are what eventually this is what we expect the grid to look like. We expect it to be highly decentralized. You're already seeing a lot of aspects of this decentralized grid in your system because you are adding a lot of distributed generation, your rooftop PV, for instance. There is more uncertainty and variability in power output. It's not like uncertainty and variability did not exist in the past. It did exist. It existed in terms of the uncertainty you would get from power demand. But now there is uncertainty and variability coming out of your power generation as well. There is less natural inertia. Your solar plants, the new wind power plants, they don't provide natural inertia to your grid as your machines used to in the past or currently as well that they're providing you. And finally, your inverters, they don't provide you as much current as a synchronous machine would under fault conditions, so you have low short circuit current. So as a result, what has happened is that there are certain challenges that we need to address. The first one that I think most of you are very well aware of, is how do we deal with this variability and uncertainty of renewable energy? Not only does output change with time, but we are also not 100% sure how much power output we would get at a given time. So that's what variability and uncertainty represent. And that creates a challenge for the power system operator because the power system operator needs to ensure that load and generation balance is maintained at all times. From milliseconds to hours and beyond, this balance should be maintained. Secondly, what we're doing is as we are adding, or at least as there is more talk about adding energy storage resources, those also happen to be energy limited resources. I can only obtain energy from a battery storage asset if I can charge it. If I cannot charge it for whatever reason, let's say there are two lines coming into a battery's substation, the lines are out for some reason, I can't do anything for my battery to charge it. Even if one line is out, I can only charge it at a smaller rate, for instance, than I could with two lines. So those are some issues that we need to start to grapple with. Inertia, I said, is suddenly reducing, and I also talked about this protection concerns arising because of low short circuit current. So all these issues are coming up, and what that means is that we need a grid that is much more flexible than what we are used to today. And these challenges are the reasons why in larger systems, you still don't see too much renewable energy being added in the system, along with, of course, the cost of increasing renewable energy penetration in our power grids. So if you see this figure, there's a figure that we worked on when I used to be at the National Renewable Energy Laboratory. So this probably keeps on getting updated. So what you see here on the x-axis is the size of the system in gigawatts. So on the left-hand side, you have very small system, very small islands, and then you move to interconnection-wide systems on the right-hand side. On the y-axis, you see what is the percentage of variable renewable energy, wind and solar in particular. in these systems. The circles represent how much is the penetration by energy, and the squares tell you how much is the penetration by power. So that's a very important distinction that needs to be made. Because when we talk about renewable energy penetration, we need to be very careful in terms of what metric do we use to define it. If it is power, what we are saying is, if at any given instant, let's say now, how much of my electricity is coming from renewable energy versus conventional generation resources. But in terms of energy, it's going to be lesser over an entire year than what it can be at any given instance of time. That is why what you see in this figure is for a very small island like the island of Tau in American Samoa. It pretty much has a set of solar panels and a battery storage, and that does the job for it. So you can just power this island with only solar and battery, and so it's 100% renewable energy system, both in terms of power and in terms of energy. We go to a slightly larger system like the King Island in Australia. It's roughly 5 or 6 megawatt system, and you see that in some hours of the year, you get 100% power from renewable resources. But if you take the average over the entire year, it's only 65%. And as you can see the trend, as you start to move toward bigger system, you see that the percentage penetration by energy starts to become much, much smaller than for very small systems. And that percentage by energy is also smaller than what instantaneous power output you get from renewable resources. And the reason why these numbers are important is because what we have found out, or when I say we, it's not just me, it's all the people who are working on grid integration research, is unless you get to these 50% levels in terms of instantaneous penetration, and more importantly, in terms of energy, only then you start to see major challenges to grid reliability and the need for major flexibility in our system. If you look at where India stands today, we are roughly at around this 10% mark from wind and solar, slightly higher than that. And in terms of instantaneous capacity as well, we might be slightly higher than 24%, but we are not yet in terms of energy close to this 50% line where we would start to see the challenges. So right now, our ability to integrate renewable energy in the grid is very much helped by the fact that we are plucking the low-hanging fruit. We are able to easily integrate these current levels of energy in the grid. But if we look at our targets for 2030 and beyond, it will get progressively more challenging to do so. This is an example of a work that we did for an Indian state, where we looked at how does its energy mix change and what implications does it have on the power system. So if we look at this curve on the top, what we are seeing here is that for how many durations do we get below the minimum solar generation capacity, like 55% of the installed coal capacity, which is the minimum level at which coal plants are allowed to operate. For how many hours in the future would our net load go below this value? And that runs into several hundred hours in not so distant future. And the reason why that happens is clear from this figure, where this gray line tells you that your load has been substantially reduced by the amount of solar energy that you are generating. Because right now we are assuming that there is no control on solar. We are only curtailing solar if there are reliability concerns. Otherwise, we are injecting as much solar as we are generating into the grid, so we can, increase the percentage of solar generated energy and its use. Now, the challenge that it creates for you is there's a very sharp down ramp. You can see the power is going down from 16 gigawatt all the way down to around 7 gigawatt. So a 9 gigawatt drop in 6 to 7 hours. And then it again goes back up in the evening time to around the same levels. So you need resources that can quickly ramp up and then quickly ramp down in order to meet this kind of variability that solar is going to induce in the systems. Now, this particular state was not an isolated system. It was part of India's larger grid, so they don't run into any issues. But the overall challenge, as other states also adopt more solar and wind energy, would increase for the grid operator as solar penetration goes up in our system. And this has been the trend in terms of ramps over last several years that has been noticed by others as well. So this is a graphic from Grid India, what used to be POSOCO earlier. And you can see that the ramps have continuously gone up from 2008 to 2020. And these RAMs will only go up as we add more solar and wind in our system. So we need resources that can keep going up and down very frequently and at a much faster rate than what we currently are able to in our system. So all that means is that we need to really value flexibility in our grid. We used to value flexibility in the past as well. We still value it, but the importance will go up much more because of all the reasons that I just discussed. And what are the various attributes of flexibility? They are startup time. So how much time does it take for a resource to start from a cold start condition, from a warm start condition, if we talk in terms of coal power plants? How fast can it ramp up to its maximum capacity? How fast can it come down? What is its minimum generation level? What is its minimum uptime? And how fast can it be shut down? So all those attributes of flexibility are very important. So what we really want from a resource is something that has a very small startup time, almost vertical line integrating instantaneous ramping to maximum capacity, faster down ramps, very low minimum uptimes, almost zero or maybe even negative minimum generation, and shutdown times also that are very fast with minimum downtimes. So just make all these inclined lines vertical and just shorten the horizontal lines, and that is the kind of flexibility that we need. So when we talk about flexibility and the resources that can provide these kind of attributes to you, in the Indian context, hydropower plants, pump storage hydro, gas turbines, we don't use much of it because of the cost of gas being quite high for India, and battery storage and virtual power plants. So these are the various assets that could be utilized to provide flexibility to our grid so that we can integrate more renewable energy without affecting our grid's reliability. And you can also see that there is a strong interplay between how much flexibility our grid has and what is the storage need for us. So we are currently doing some simulations where we are just trying to see what is this interplay. And we find that for all those different attributes that I just mentioned, if we increase the flexibility by 10, 30, and 50%, for instance, for a system that reflects similar conditions as you find in India in terms of the inflexibility of generation, you see that we need less and less of energy storage. So when we start to go about identifying how much energy storage do we need, we also need to make sure that we fully understand what are the other flexibility resources and capabilities that are available in the system, including demand side flexibility, because there is a strong connect between all of them. So before I move to the next section, again, I'll just stop here for a second and just ask in case there's any question about the part that I covered earlier.
Anyone who would like to ask anything?
Because I can keep talking, but
yeah,
yeah,
sorry, I
go ahead.
joined late. This is Avinash Manji here. Hello.
Yes.
Yeah, we can hear you.
Yeah. So essentially, sorry, I joined late. So essentially, decentralization of power means like using of renewable energy and like avoiding too much dependency on the fossil fuel, or like so
Yeah,
is that the crux? Yeah.
Yeah, I mean, decentralization essentially means that your generation is no longer confined to. Hello, can you hear me?
Yes.
Yeah.
We can hear you.
Yes.
Yeah. Okay. Great. Yeah. So when I say decentralization, what I mean really is that we are not confining ourselves to power being generated from very large power plants alone.
Yes, I can consider it.
I'm sorry. I think someone.
Yeah.
I'll just.
Yeah. I'm saying I can.
And we rather would like to produce electricity from distributed energy resources like your solar PV, for instance. So your center of gravity of generation will start to move from high voltage transmission system closer to your low voltage distribution systems. So that's what I mean by decentralization. Instead of one large plant, you might have several very small plants in the system.
Right. Okay. Thanks.
But it is a consequence of the fact that we are adding more renewable energy, so that at our homes there is no emission while we are producing electricity.
Right.
Okay, any other question before I move? Okay.
I just sorry if I can interrupt at the last
Yeah,
minute.
please.
I just put in a question in the chat box. I too was a little late in joining. My query is that with so much of move towards EVs, etc., and the manufacturers talking about 80 kilowatts, 100 kilowatts, or 200 kilowatts of charging within 15 minutes or 20 minutes. What happens to the grid when, say, in the evening, suddenly people have put all their cars on charge?
Yeah, I mean, if you don't plan it, terrible things could happen.
No, because I think it's a serious matter.
Yeah,
Everyone has to look at it from that aspect too. But is there something which, with your experience and vast knowledge, have you given that a thought in terms of how it's possible to overcome such kind of thing? Because we don't want the system to collapse. And
exactly.
One second.
Yeah, so you are absolutely right. I mean, if we, as we add more electric vehicles in the grid, and those electric vehicles have fast charging capabilities, we'll be putting a lot of load on our distribution systems first, and then it will automatically transfer to our high voltage transmission system as well. So there was a study that I was part of. We were looking at the reliability of the electric grid if the city of Los Angeles transitions to 100% renewable energy by 2045. And there, this idea of high electrification of our transportation sector also came into play. And that demand was added in our subsequent analyses. So, as I said, what you need are definitely resources that can ramp up very fast. So you would need a lot of generation than in terms of installed capacity, your overall generation levels go up substantially, because you probably won't need them all the time, but you still need them when your load goes up, like with this electrification of electric vehicles you mentioned. So you would need to account for it. You can manage this, but you would have to spend a lot of money to build in that flexibility, so you can ramp up resources on a very short notice, because you don't need them during the daytime, but you probably need them in the evening time when people have come back and started charging their vehicles. So at what exact time you would need these resources is also a function of when do you incentivize charging of electric vehicles. So that depends on what kind of load curve do you get, but you still need a substantial amount of capacity to meet your electrification demand. So as I mentioned, deep electrification is going to create a lot of stress on your grid.
So on one side we are looking at clean energy. On the other side we're looking at a demand which is going to be huge.
Yes.
As I understand.
Yes.
It's a catch. It's going to be a catch-22 situation.
Yes, it is going to be, certainly.
So we don't know whether the auto guys need to look more towards hybrid or then to look towards only EVs. Anyway, that's a separate topic. So I'm sorry I interrupted you.
No. It's a very good point. And the reason why. Yeah, please. I mean, the reason why it's a very important point is because it highlights the importance of investing in planning well ahead of time. Because whenever you plan, and if you don't take into account these kind of situations that may come, a decision taken today would only come to fruition in 10, 15 years. Like if you're expanding a transmission network, building more generation capacity, the better we do the planning, the more effective our results are going to be. And it's not just about energy balance. I think that's something that I want to really emphasize. It's also about how do you make sure that your electricity is actually transferred from where you're generating it to where it is to be consumed. And that's where the transmission
Agreed.
system, voltages and things like that, they come into play. So if you only do load generation balance, which is like a lot of the studies do look at that, and we don't consider the operational issues and how we actually can move this electricity, then we might run into issues for sure.
Thank you.
Yeah, sure. So because of this the need for flexibility, different people in different parts of the world have started to talk about getting flexibility from buildings. Grid interactive buildings, grid interactive efficient buildings are some of the terms that have been used over the last few years on how can buildings where really the actual energy consumption takes place can play a role in creating more flexibility in our system. Because the reason for the grid to exist is this demand in the buildings, pretty much, or in our industries. So if we can modify a demand, overall behavior of the grid also ends up changing. So these are some of the key characteristics that you see on your screen of a grid interactive efficient building as per the US Department of Energy. So we want to add more efficiency in our appliances. There should be two-way communication, so I can interact with my utility, can interact with the customers, obtain some flexibility from them. If we have smart appliances, analytics, we can make this process of flexibility easier. And really where we really want to be is we get a flexible load, not something that can just respond to our demand, but maybe even autonomously sense grid conditions and respond to our grid needs. So those are some of the things, especially the last part, that we can sense the grid conditions and respond to the requirements of the grid, is what I'll talk about in the next few slides. The other aspect, as the gentleman just highlighted, was that in India, not only we need to decarbonize, but at the same time, we need to tackle this huge growth in energy demand that is going to come up. I mean, if you just take the case of air conditioners, I mean, roughly 13% households own an air conditioner today. And this is going to significantly go up in the next 10, 20 years. We're already seeing how temperatures are increasing, and the need for cooling load, need for cooling is only going to go up. And as people get more money, they get richer, they would be willing to buy more air conditioners. So there is a challenge that there is a lot of demand coming up, and we need to meet it through resources that are variable and uncertain. But there's an opportunity as well. And from that I, as a power systems engineer, as an electrical engineer, the opportunity that I see is in the loads that are equipped with inverters. Because inverters, they give me a lot of problems, but at the same time, they give me a lot of opportunities as well to model the behavior of a resource the way I want it to. So there's a lot of flexibility that you can get. If you can program these inverters well, you can obtain a lot of very nice behaviors that are supportive of the grid and support grid flexibility and integrating more renewable energy in our system. So one of the examples that I'll talk to you about is what is called conservation voltage reduction. And if anybody has been in the utility business for the last 2-3 decades, they may recognize that conservation voltage reduction has been used for at least 3-4 decades by utilities to force demand response. They would change the voltage right at the substation itself. The voltage goes down. A lot of our loads used to be simple resistive loads. You can remember your incandescent bulb of the past, or your water heaters, your space heaters. Your voltage is down, you get a power reduction in square of the voltage terms. So it was pretty effective. People used it quite effectively in the past. What it was not very effective for, and of course it's not effective for today as well, is for loads that take constant power. You reduce the voltage, current goes up. And if current goes up, if you remember from from our 10th, 11th physics as well, your losses go up by square of the current. So you might get no reduction in your power demand. In fact, you might see a slight increase because the losses have gone up. So it's not very effective for loads which are constant power loads. And the problem for us now is that, well, most of our loads are becoming constant power loads. You look at any modern appliance, whether it's your lighting, LED lighting that you're using, your inverter air conditioners, your inverter fans, your BLDC fans that you talk about, pumps, they are all increasingly becoming inverterized, if you will. So these act like constant power loads, and the effectiveness of conservation voltage reduction would go down. But are there ways in which we can still use these assets and provide some power reduction? So that's what we started to look at. And this is a figure that looks quite complex, but it's fairly straightforward. On the right-hand side, where I use my pointer, here is a simple model of your refrigeration cycle or air conditioning cycle. And we connect to it a model of the induction motor that is used in your air conditioners. And what we do as a result is we change this voltage, and we observe how much power demand changes or how much energy demand changes over a period of time. We do one more thing. We not only change this voltage, but we also change the frequency of this voltage supply. And then we compare which gives us more reduction in power demand, or do we get power reduction at all? So here's what we have found through our simulations. So when we do just simple voltage control, and we reduce our voltage by 10%, we increase it by 10%. What you see is your energy savings are rather, they are negative, meaning that you're actually ending up consuming more energy as your voltage is reduced. Your COP is also not changing much. Changes are in the second decimal place. So effectively, there was not much use of this just simple voltage control. But if you change voltage and frequency in the same ratio, if I change voltage by 10%, I do the same thing to my frequency, which is most of your inverter air conditioners do these days, or at least are capable of doing these days. You see that the behavior changes. Now, as I reduce my voltage, I do see a few percentage savings in terms of my energy. Now, this was all simulation, so we just wanted to test whether it makes sense in an experiment as well. So we put together a simple air conditioner. This is a conventional air conditioner, not an inverter one, but we can make it an inverter air conditioner by using this programmable power supply. It can change the voltage, it can change the frequency. I'll just show you in a video how it can do that. And we observed how much power did we see changing in the air conditioner's operation. So here's what you see is the supply connected to air conditioner. At 220 volts is the supply, and 50 hertz is the frequency, which is what we get. And you get 840 watts of power being consumed by this air conditioner right now. Then we reduce the voltage by 10% and the frequency by 10% as well. And now you see that we have our power demand has suddenly gone down by about 100 watts. So 100 watts in an 850 watt system is a decent amount of power reduction that you instantaneously obtain if you change both voltage and frequency. So when we did a few more experiments, what we found was that if we keep voltage and frequency ratio was kept fixed, then at different voltage levels at 0.9, 0.95, we saw about 5% difference in our energy consumption just by controlling the voltage and frequency. Now, the question is, how do you change the frequency? Frequency is set by the grid. So how do we change that? And that's where the inverter comes into play. Inverters always come with a chip, with a digital signal processing chip, where I can decide what code I want to put in. And there I can make the changes, and I can make sure that if I give a signal to this inverter to do CVR, it will not only change the supply output voltage, it will also change its frequency. So through that process, we can still get benefits of CVR. Each AC could respond differently, get different amounts of power reductions, but there's a possibility of doing it without changing anything on the grid side of things. So before I move forward, let me just stop here because this is probably a bit a lot. So if there are any questions, I'm happy to answer before I move on.
Sorry, I think I seem to be the one who's raising stupid questions. But
yeah, please go ahead.
I just wanted to check with you this inverter which you're talking about for both controlling the frequency and also the voltage.
Yes.
What kind of a cost are we talking about? Because you see, if you're feeding, say, typically everyone is familiar with a 1.5 ton air conditioner, and normally, you're looking at almost about, though you're showing 840 watts, but when you kick it on, it is higher. So you will need to have an inverter which can withstand that startup load.
Yeah.
So let's say it's a 1.5 kilowatt inverter. With this, what side of a cost are we talking about? So, because today everyone, sure, please go ahead.
Yeah, so what I wanted to say here is that all the inverter-based air conditioners that you're getting, they all have inverters that can provide you that amount of power. So that inverter is already there. That control card is already there. The question is, what kind of algorithm do I add in that control card?
Use. So because I mean, as a user of air conditioner, we have all these inverter-based compressors, etc. But as a user, can I make the changes?
No,
because
user
I don't.
No. User won't make the changes. User can't make the changes.
That's exactly my point. And here we are talking about that. If we want to make the change, or are we suggesting that we ask the manufacturers to set in into their inverters that this is what we are looking at?
Exactly. That's the idea. That if we do this research and we see the benefits,
so then I have a small question. I want to know, because this is something very interesting. And to do this, it'll have to move through BEE.
Yeah.
And is there anybody in your organization who is taking forth these new things to discuss with BEEs, so that BEE tomorrow can put in a clause like, there was this star rating thing which came up many years ago, but it took a while for BEE to impose the star rating.
Right.
So this is another step which I am quite sure with the someone will have to look at it, because it sounds very interesting. Everyone save on energy. The government wants to save on energy. The user wants to save on energy and cost, etc. And this is a very, it's something which needs to be really looked at.
Right.
So the challenge with Reliance is that here you're talking about energy on one side, and then you're talking about planning for the future, keeping the EVs in mind in terms of how we are going to keep our backups ready.
Yes. And you're right. We need to take it up. I mean, the reason what we still need to do is, and that's what we're working on, is just to evaluate this under more conditions which are more climate controlled. Like we fix the ambient conditions, we fix the weather, the temperature and the humidity, and see how much savings do we get under different conditions.
Sure.
So I think this has to be taken up. If you say in our organization who needs to take it up, it's probably me who need to do it.
Because you see that's exactly the point, because you'll need to have you'll need to really have someone build up a team to take it up also.
Right, exactly.
Humanly, it's not possible.
Yes.
And the fact is that these are the new challenges which the government also needs to know.
Right. No, I mean, so
anyway,
through you, through you, I mean, those are the things that we want to spread out and see if there are ways in which this could be worked upon further.
Oh,
I
I'm
think
quite sure that.
Manish
Yes.
was also raising his hand.
Yes.
Yeah, thank you. Thank you, Ansu sir. I have a query regarding one thing. Like
Yeah.
we are using the inverter technology.
Mhm.
So inverter will causes the harmonics. Total harmonic
Mhm.
distortion will
Yes.
also affect the power quality
Yes.
parameters.
Yeah.
And the second thing, V by F control
Mhm.
is basically wherever the variable loadings are there.
Mhm.
See, our outputs are variable, then we can use this voltage or frequency control. So, in case of AC air conditioner, you are telling that. So, if we do V by F control, then our uh, COP and this terms of refrigeration also will affect. So,
Right.
we'll reducing the voltage and frequency, then automatically our uh, output will reduce, and power
Yes.
is power also is reduced. So
Yes.
my aim, I just wanted to convey that this is used only wherever the variable loading is there. Where is the constant like BLDC fan? We can't use this because there is a constant flow of the fan, CFM of the fan. So it is good to use it here, but it can also scale up to the large industry wherever the motor loadings or pump loadings or air compressors,
Right.
wherever it's going on off. So then we can use VFD, variable frequency drives, for the power saving purpose. Thank you.
Right. 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 Yeah. Yeah. You're right. I mean, like right now, what the way we are using variable frequency drive is to, get more efficient air conditioner performance under variable loads. This is not a solution that you would run in such a way that you create discomfort for the end user. So it's not going to be something where you apply 10% reduction in power for 2 hours in one go.
Yes, not at
But
the cost of human comfort.
not at the cost of human
Yes,
comfort. But there are
correct, sir.
there are situations, for example, when we talk about primary frequency response from the grid, which needs to be provided within 30-50 seconds time frame. If conventional resources don't provide it, then renewable energy resources have to provide by reserving a headroom. That means you're spilling energy. You're not injecting it into the grid. So in those kind of situations, in a minute's time frame, you can use these. Or if the utility wants to reduce its peak power because of whatever reason, let's say EVs or weather, the summer temperatures being quite high, in those places, these kind of solutions can play an important role. So it's going to be a series of solutions, not just one that provides all the benefits. So I do get it.
Correct, sir. So what about this harmonics? Because of the
Harmonics,
inverter,
yeah.
it should be inbuilt active harmonic filter attached with this inverter technology.
I think even the passive filters do a fairly good job. Like the power supply that I showed you, uh, that is also basically an inverter itself. And it also I don't think it has an active filter. It has a passive filter alone, and its harmonic distortion is almost negligible. I mean, if you look at its output waveform, it's almost purely sinusoidal waveform. So they do a fairly good job. Like so far, having done all these different analyses over the last 8-10 years, I haven't seen a case where harmonic distortion is a limiting factor for adding more inverter-based assets, whether on the load side or on the grid side. Now, one can argue that we are still not at a very high penetration of these resources. So I would definitely take it as a point that this is something we need to keep monitoring as we add more inverter-based assets. But I haven't come across any study where total harmonic distortion has become a limiting factor for adding more such resources.
As per IEEE 519, voltage harmonics should be less than 2.5 and current should be less than 5%.
Mhm.
So if we talk about the high energy intensive industries like
Mhm.
refinery, petchem, railways, there
Mhm.
it is one of the important factors. Also, in Tamil Nadu, there is penalty of TDD losses. So it is also to be considered into account, because all the railway tractions are running and they are creating this harmonics.
Okay.
Because
Yeah,
they also have that train also have the regenerative current braking system, regenerative braking system. So the reverse current also creating the harmonics and it is stored. Yeah, sir. Thank you.
Yeah, right. I mean, then on these kind of cases, you need to do those detailed electromagnetic transient studies to figure out how much distortion do you get. Because if you do some steady state studies that people typically do, that alone is not going to be enough for these kind of analyses. So for those specific situations, these kind of studies may be done. And I think there are ways available to address those issues of harmonic generation.
Okay, sir. Proceed, sir. Thank you.
Thank you. All right. So the other thing that we did, and again, it originated at NREL, was how can we manage our load so we can provide support in this kind of time frame? 1 second to 10 second, 10 to 30 second time frame without requiring any communication. So with no communication, can I still vary my demand and manage my grid better using these these demand side assets? That's when we came up with this idea of grid supportive loads, and it's also in a paper that we had published. And the idea was that, well, we are using these inverter based assets. They have a controller, they have a chip. I can program it to do whatever I want. So I can even measure frequency locally. I can measure voltage locally. And frequency is a global measure. That means if you measure the frequency here, under steady conditions, the grid frequency across India is largely going to be the same. There might be small variations, but largely the frequency is going to be the same. So if you measure voltage, if you measure frequency locally, then can we change our power demand and provide support to the grid? So we did some grid scale simulations, assuming that this kind of response to variations in frequency can be provided. So we took a system, a synthetic system representing ERCOT. It was not an actual ERCOT system, just a synthetic representation, artificial representation of that system. 60 gigawatt load was there, and we added around 1100 loads at the transmission level, which could provide this kind of frequency-based modulation of power output. And what we observed there was that our power demand, we could change our power demand by up to 2000 megawatt for every 0.1 hertz change in the frequency. And 20% loads were assumed to be grid supportive loads. So what does that all mean? What it really means is that, like a generator which has droop control, a governor, we would add a governor to these loads as well. Each inverter has a maximum minimum current. We will limit it to that. And then we can decide for how much time do we want to provide this kind of support. As I said, frequency response in this time frame is like 20, 30 seconds, 40 seconds, not more than that. So if we do provide this capability, we can take the frequency from 59.9 all the way to 59.96 hertz. It looks very small, but it's quite large for a grid that is of ERCOT scale. So those are the kind of impacts we could get if we are able to obtain this droop kind of response from our loads. And again, inverter-based loads is what really helps us achieve that. Now the question was, well, if you do implement it, how would you implement that? So we have been working on implementing it in appliances as well. So again, using the similar setup that I'd shown you earlier, we dropped our frequency instantaneously from 60 to 58.5 hertz. I mean, you can do 50 and then take its 5%, makes no difference to the simulation. 60 or 50 is the same thing for us. And our power demand, as you see, was roughly around 380 something kilowatts. And in about 2 seconds after the drop of frequency, it became around 180 or 190 watts. So the power was halved in about 2 seconds to give us this kind of support to our grid. Because unlike a generator where we would increase our power demand, here we are reducing our power demand to get quick response from the grid. So this is something that we are now working on validating in hardware. And we find it really attractive because we don't need any communication infrastructure to make this kind of load changes in our system or create this kind of flexibility in our system. So these are some of the things at faster timescales that we are working on in terms of getting this flexibility from resources, which is not something we generally talk about whenever we talk about demand response in general. So again, I'll just stop here for a second in case there are any questions before I move on. All right. If there are no questions, then one more thing I want to show you again. So I'm just trying to give you some snippets of the things that we are working on, which I think you'll find interesting and which are slightly non-conventional because we have the mandate to go after these kind of things as researchers in academic settings. Then this is another piece of work related to demand side flexibility, which we called price responsive loads, that we worked on again when I was at NREL. And here we used some detailed modeling. We don't want to get into what is integrated T&D modeling and stuff, but we did some detailed modeling of both transmission and distribution systems, and we wanted to see what happens to the demand at the transmission side if real-time pricing is made available to the loads, and how much reduction in power and in prices do we observe. This is a very small sort of test system that we had, very simple 5-bus system, very widely used in research community. And at each bus, we added a lot of these distribution feeders. So these are like distribution systems, radial system that you would find in actual implementation in the fields as well. So we had around 1,000 megawatt of load that we added in the system to see how price responsive loads are. To run this simulation, we had to use the supercomputing facility, high performance computer. At that time, it used to be called Peregrine, to run these kind of simulations because, believe me, they get very, very complex even for a 5-node transmission system, because the number of distribution nodes become extremely high. Here, the price responsive behavior was very straightforward. You had a desired temperature that you would just modulate based on what is the price differential in the last 2 time points, and a historical average represented by the standard deviation of the last 12 hours prices. So how much would I want to change my desired temperature would depend not only on what the current price differential is, but also what was happening over the last 12 hours or so. And there was a maximum limit of delta TH and a lower limit of delta TL that I would change my temperature by. So then when we started to look at all the different feeders where we implemented price responsive demand, we could see a substantial amount of reduction in power requirement from the grid as a result of these changes in the prices. So especially during this daytime period, we saw most of the changes coming in our demand. But when we tried to spread it out over all the buildings, we had around 9,000 buildings in our model that we were simulating. The percentage change in the demand for each building was not very high. And I think that's something a lot of people have also seen in literature, which I'll just talk about after this slide. What people have witnessed in terms of pilots on how much power demand reduction they are witnessing. So in some cases, some consumers also saw a slight increase in their power demand in the system because of the way voltages were changing in the grid. So we were able to simulate it, but we didn't see a huge amount of power reduction for the various customers in our simulations. So this brings me to the last part of the presentation. So we have seen, like, why do we need flexibility in the grid? What are the challenges that adding more renewable energy provides to the grid? What are some ways in which demand side assets could be used to provide flexibility at different time scales? the latest simulation results that I show you, they were more about hours level kind of or several minutes level timescales. And we also saw something that could provide you response in seconds level timescale. So multi-timescale demand flexibility is what you could get. So what are the various regulatory and policy aspects of getting this demand flexibility? Because unless you have the right regulations, right policies, right incentives, it's very difficult to realize the potential of demand flexibility. So it again brings us to this time continuum of system balancing. So whenever we talk about providing flexibility, we should always look at what are the various time scales at which my asset could contribute to flexibility. So currently in India, secondary response and beyond is what is available for demand side assets to provide support as well. With the 2022 regulations, even demand side assets are eligible to provide secondary frequency response and fast tertiary response in these time frames. There is still a market to be developed for inertial and primary frequency response, so that is still not there, but I am fairly sure that as you need more flexibility, even this would come up in the next two or three decades. The most relevant regulations, at least to the best of my knowledge, are the Central Electricity Regulatory Commission's Ancillary Service Regulations of 2022. They were notified fairly recently, roughly almost 2 years ago, and they incentivize all the resources. So they don't make any distinction between generation or demand side resources, and they want you to provide ancillary services at seconds level time frame, very much like your automatic generation control or AV generation control, and at slightly slower time frames, which is characterized by this TRAS or tertiary response ancillary service. The requirement for secondary reserve ancillary service is that the entity that is providing the service should respond to the signal within 30 seconds. And then the entire obligation, that is an entire output that it needs to move up or down, should be provided within 15 seconds, which should be sustained for 30 minutes. So those are the criteria that you need to fulfill before you can provide the secondary reserve ancillary service from demand side assets or from generation assets or storage asset. So as I said, it's agnostic to the kind of resource that is available to you. For tertiary response reserve ancillary service, you need to respond within 15 minutes and then sustain it for the next 60 minutes. So these two are the services that these regulations enable. So as I said, demand response is eligible to provide SRAS and TRAS. The only thing to note here is that there are incentives and penalties for not adhering to the promise of delivering some demand. If you give a performance that if you're able to comply with the signal more than 95% of the time for SRAS, you get 50 paisa per kilowatt hour incentive. Maybe not a whole lot, but that's what it is right now. But if you perform below 20% for 2 consecutive days, then you will not be allowed to participate in this service for 1 week. So one of the major issues that we came across when we were working on demand flexibility is how do we ensure that from a building we are able to provide X amount of megawatt at Y hour. So let's say 10 megawatt from a community at 9 o'clock or 2 kilowatt from a house at 8 o'clock, something like that. So that is something that we were working. This was my last project at NREL before I left. So that's something we were working on. That how do we ensure or give confidence intervals around how much flexibility can I provide you at any given time? So maybe lower amount of flexibility with high confidence, and higher flexibility with lower confidence. So now an aggregator has the choice to decide which option to go with and bid in the market. So this is something that needs to be accounted for, in my view, that if we can handle this uncertainty of realization of demand flexibility better, then there are options starting to open up even for these demand side assets to provide flexibility to the grid. Tariffs play a very important role in ensuring that this flexibility is actually realized. So I'm sure a lot of you are aware of these time of use based tariffs. for electricity consumption. There are various varieties of them. One is fixed price, where the period and the price of time of use rates is fixed. And then you have dynamic pricing, where real-time pricing could be provided, or the peak price could be different at different times, or there might be a different price for critical peaks that a utility declares. So these are some of the curves that show how these various types of prices are different. For a time of use based pricing, the peak rate is different, it's generally higher. The off-peak rate is different, and the period is fixed when these prices would be applicable. For real-time pricing, the pricing is almost always changing. Generally, you get prices being declared at every hour, but you can have even smaller time intervals. In variable peak pricing, it's really the time period is fixed, but the peak price is something that can change. Whereas in critical peak pricing, the only difference is that the peak price difference only comes when a certain critical period has been declared by a utility. And then instead of price, you might even provide rebates. The tariff is fixed, but on certain critical events, you might provide rebates if you reduce your demand, if the need is for reducing demand from the utility. So those are the different time-based tariffs that have been used by different entities across the world. And what you need for them to work? Well, you first need to know, will the customer respond to these price signals? And there is various factors that can go into answering this question. Can the customer easily access their usage? Assess the various options that they have and identify how much benefits will they get. Those could be one way in which they will respond to price signals. Do you have the smart metering and the AMI infrastructure, the advanced metering infrastructure available to send the prices to the consumers on a periodic basis? How much automation do you have? Because the less customer involvement do you have, the more likely their response is going to be, because it's less hassle for them. And then how do you design the program and how do you do your outreach has also been found to be important. As you'll see in the next couple of slides, opt-in approach versus opt-out approach makes a lot of difference in the design of the program. So in opt-in approach, the idea is that you give people a choice that they can participate in the program. In opt-out approach, you enroll everybody and then give people the option that they can go out of the program if needed. So the latter approach has been found to be much more effective than the former one. And what also plays a very important role is how helpful the utilities are in helping the customers adopt the time of day rates. If you leave it on autopilot, the performance is unlikely to be very, very good. So if you look at some of the examples across the world, PG&E, which used to be Pacific Gas and Electric, they had these time of day plans for commercial customers. It's optional for residential, at least at the time when I made the slides. And they had 4 different prices that they had created: peak, partial peak, off peak, and super off peak. One of the important things that they had noted was that their renewable generation has shifted the peak loading from 4 to 9 p.m. to 4 to 9 p.m. from noon to 6 p.m. earlier. So this reduction in the demand in the daytime, they were already witnessing, and that's how they decided to change their peak pricing hours based on when the peak was actually happening. There were pilot programs in Southern California Edison and PG&E. So they saw a load reduction of about 2.7% and 6% respectively, but you don't see a very big difference in the bills of the consumers. And that's something that you'll keep finding in some of the other examples that I present, that it's the peak demand that reduced quite a bit. The overall energy consumption did not come down significantly, and as a result, the consumers didn't see a huge difference in their electricity prices, which sort of tries to suggest that it becomes more and more challenging to enroll people and help and enable them to participate in these demand response programs. So what SMUD, which is the Sacramento Municipal Utility District, the conclusion they came to was that while it would not necessarily help them reduce rates, it might prevent them, or it might avoid them to raise them further, or the reduction could be less. So this is just an example of how much average reduction of different quantities they saw: carbon reduction, peak load, the average customer bill. So again, not a huge amount, like $3 per month or 2%, not not a whole lot. It depends on who you are, what the different what your financial condition is. It may or may not nudge people to be very enthusiastic about these programs if price customer bill reduction is the only factor that we are considering. And then you see similar results in Pennsylvania, Colorado. Peak demand reduction has been quite significant, but again, the energy consumption and the bill reduction has not been tremendously high. Moving to Europe, they have also done some pilots to figure out how much benefit different customers get. In Italy, for instance, in one pilot, they monitored 28,000 customers, and they saw a modest shift in consumption, about 1% from peak to off-peak. And 60% of the customers, however, moved their consumption. And one of the reasons why they didn't see too much difference was because there were high off-peak electricity prices before the time of use tariff was implemented, and there was a very small differential between peak and off-peak prices. So that suggests you that this differential really matters on how effective the program is going to be. In Germany too, the peak demand changed. There was no change in the off-peak demand, and they observed that the peak demand was shaved but not shifted a lot. So even with a price differential of about 200%, they didn't see a lot of shifting in the demand, but rather shaving of the peak demand. Similarly, there were surveys conducted in UK on TOU trials. The peak demand reduction was again modest, but few persons faced higher bills as well. It just depends on your ability to shift the load. If you're not able to or not reduce the demand at the peak instance, then you will see end up paying higher bills. So what are some of the key takeaways from these programs? The key takeaways were that peak demand reduction was much higher compared to energy and carbon emissions reduction. Consumer bill savings were much more modest. Some customers even observed some increases. So that's a challenge for creating a right incentive for people to participate in these programs. As I mentioned, opt-out approach was much better. The enrollment rate and people's rates for continuing in the program was much better if you enroll them in the beginning and then give them the option to opt out if necessary. What was also very critical was that how much customer outreach do you do? How supportive the utility is in enabling customers to participate in these kind of programs. So that was also very important. And what people are expecting is that as this AMI rollout happens, people want to move towards more time of use tariffs and even dynamic pricing. So that's the trend that we're moving towards. And perhaps that is what explains that recently in India also time of use rates have been put on a schedule to be implemented. I think you may have seen this notification that came out some time back. The tariff during peak hours would be 10 to 20% higher. The idea is that you move your demand to the solar hours, so you use more solar energy. There is less curtailment. It is going to be applicable to commercial and industrial customers by 2024, 1st April, and to all consumers by April 2025. If there are customers with smart meters, then this might become applicable immediately as well. So what we are really seeing is that there is an interest in moving the demand and creating flexibility. It still remains to be seen how much is that push and how much people are able to move it. Because if we only try to use reduction in power in customer bills as the motivator for people to move to flexible demand, it's going to be a bit more challenging. So if we want to decarbonize our energy systems, we need deep electrification, which requires you to make your grid more flexible, and that's where demand side can play a role. And as I've shown from some of our work in the current work and past work, demand side can provide you flexibility at multiple time scales. The more automatic and autonomous you make it, the better it is, because then you don't require customer intervention that much. And if we want to incentivize customers to participate, we need to find out how do we monetize other benefits of demand response, whether it is reduction in deploying more energy storage, a lot of which is imported. So there are strategic benefits, indigenization benefits, there are benefits to just decarbonization in general. So how do we monetize all those benefits and then present incentives to customers based on all these benefits is, I think, key in ensuring the demand response can play a critical role. And finally, if we don't do modeling well of these resources, we won't know what value they provide. We can't quantify this value. And this modeling should happen looking at all the different elements of the power grid, not just demand supply, but the grid that makes it possible to generate electricity and deliver it to your consumers. So I think with that, I'll just stop here and just open the floor for any further questions that you may have.
Anyone with a question? Would someone like to? I think your presentation was so good that no one has any query.
Yeah. I mean, it could be that, or it could be the other way around too. So it could be either way. I think I can stay around for 1 or 2 more minutes in case anybody has questions, or they can always mail it to me, and I'll be happy to answer the questions later as well.
If anyone would like to ask anything, you have a comment saying great presentation.
Yes.
So
Okay, great. Thank you. All right. So if there are no questions, I think we can probably close.
Okay. Yeah, of course. So thank you, sir, for joining us and for the
Sure.
great presentation. And thank you to all the participants who have joined us today and have given their time. So we'll be having these webinars in the next week also, from Tuesday to Thursday. And I've put my mail ID in the, एक second, I'll do it again. So if you
And
have
I think
any questions,
Mr. Abhishek has a question. He's raised his hand at
sure.
least. Yeah.
Sure, Abhishek, you can go ahead. Your mic is not on, Abhishek.
Maybe it was an error. Yeah. Okay.
Sure. So we'll be having these webinars in the next week also. And I have put my mail ID in the box and I'll put it again. So if there is any query that you'd like to go ask, or there is anything. Also, we are looking for signatory. If you would like to join us in this initiative of the Decarbonization Business Charter, you can contact us through this ID and we'll get you with the onboarding team. So thank you, everyone. Thank you, sir, for the great presentation. It was very nice to have you here. And we're looking forward to seeing you people again sometime. Thank you so much,
Thank you for
everyone.
inviting me.
And
Thank you so
I'll
much.
end the meeting.